Habitable worlds far away from our own. You're listening to Are We There Yet? The radio show exploring space exploration. Hi, I'm Brendan Byrne. What exists beyond our solar system? And could there be life on some faraway planet? Well, that curiosity led to the first confirmation of an exoplanet in the 1990s. That's a planet that orbits another star. Decades later, astronomers and scientists have discovered over 5,000 other planets using satellites, ground-based surveys, and more. But on these distant worlds, could life exist? We'll speak with MIT's Sarah Seeger about how exoplanets are found and what questions their discoveries could answer. That's ahead on Are We There Yet? For centuries, scientists and astronomers hypothesized that planets orbiting other stars could exist outside of our own solar system. In 1992, the first exoplanets were confirmed. Decades later, with advanced technology, there are several ways astronomers find these faraway worlds. One method is the transit method. It uses a star's dimming and brightening to identify planets as they orbit in front of the star. With new methods and techniques, thousands of exoplanets have been found, and astronomers continue to explore our universe to find more. Here to talk more about this field of planetary science is Sarah Seeger, a professor at MIT. Sarah, welcome back to the show.
Thank you.
So you have made it a lot of your work looking for habitable worlds in our universe. Tell us a bit about the state of finding exoplanets these days. I know you're leading the charge in this area. How are scientists like yourself finding planets that exist outside of our solar system?
Well, the main way for finding planets today is by the transit method. Some planets are very specially aligned in their orbits, such that they go in front of their star as seen from our viewpoint, every one of their orbits. And we call it the transit method. So today, that's the most common way that exoplanets are found. We have ground-based surveys. We have our MIT-led NASA mission TESS, which studies one giant strip of the sky for a month before moving on to the next strip over and over again. And giant computers search for these tiny drops in brightness of the host star that might indicate the presence of planets. The funny thing is, every decade, there's a new planet-finding technique that comes into its own. So while transits are the best way to find planets now, that will change.
What was it before transits?
It was a technique called radial velocity. It's a very awkward name. Sometimes we call it the wobble method.
And are you essentially looking for wobbly stars?
In that method, yes. Right now, both with transits and with radial velocity, we do not see the planet directly. We just see the effects of the planet on its host star. And the wobble method involves the planet mass. As the planet and star orbit their common center of mass, the star appears to wobble, and we can measure its line of sight motion, hence radial, and velocity means its line of sight motion.
So I want to talk a bit about TESS, because this is a really interesting spacecraft, and personally, I had a chance to see it while I was in the clean room before it left, so I have a bit of a personal connection to this, and I know you do as well. What is TESS up to these days? How is it doing since its launch a few years ago?
TESS is doing well. It's in a very stable orbit, a highly inclined, highly elliptical orbit about Earth. It goes out halfway to the moon and back every orbit. And it's such a stable orbit, it's stabilized by the moon, it turns out, because on one orbit, the moon is on one side. On the next orbit, the moon is on the other side, literally gravitationally stabilizing the TESS mission orbit. So it has enough fuel to last like 1,000 years or something.
That is wild. 1,000 years of searching for exoplanets. I can only imagine how many TESS may find.
Well, interestingly, it may saturate because it can't search every single possible star that it observes because of sensitivity issues. But it certainly does have millions and millions of stars at its disposal. So it just has to get renewed by NASA every few years. It's got to get the green light, go ahead. But TESS is moving along. It's finding new planets. In fact, it's kind of surprised us in a way because some of us thought TESS would find all the best stuff first, the easy stuff to find, and that it would kind of just keep chugging along with little new, but it keeps finding many exciting new planets. The most recent TESS planet is one around a 3 million year old star, very young star.
3 million years old being young, I like that. It makes me feel young. What's ahead for TESS? What's the next campaign?
TESS has continued to, the way that TESS works, largely speaking, is it observes one giant strip of the sky for a month because it has to avoid the sun. And it sort of keeps marching along the sky, switching hemispheres every year. But right now, and I'm not closely involved, so I can't speak to any detail, but the team is trying to think of other ways to use TESS in the way that it tiles the night sky.
And has TESS met expectations? I know it was expected to find about 1,000 transiting exoplanets in its first few years. Has it reached those expectations?
Yes. In fact, when you set out to do a mission, you have to have a list of requirements that the mission is designed to. And TESS's mission, like its scientific reason of being, was to find 50 small planets, small being in this case less than 4 Earth radii, with measured masses. So finding the transits, validating that they're planets, and then getting a mass measurement, not only to confirm the planetary nature, but just to have planets with well-measured masses and radii. And TESS has met that prime mission goal.
What comes after TESS? You mentioned that methods of finding exoplanets change every decade or so, from the wobble to now transiting. What do you think is going to be the next method? Do we know what that is yet?
We do. It's a really interesting method called microlensing. It's actually called gravitational microlensing. And this method is very intriguing because we don't see the star or the planet. Remember before when we were talking about how the planet induces motion in the star or blocks part of the starlight? In this case, we actually, oddly enough, see neither, but it's a dark, an unseen star with an unseen planet moving between our line of sight and a very, very distant star in the galactic center, in the bulge. And what happens is if a star goes literally right aligned between us and that very distant star, mass bends space. And so some of the light from the very distant star that was just going off at an angle to outer space gets bent around this unseen lens star and lens planet. And the background star gets magnified for a duration. The total event could last days or weeks, and the planet event would last on the order of several hours. And this gravitational microlensing technique has been going on with ground-based telescopes. But what's happening is the Nancy Grace Roman Space Telescope, used to be called WFIRST, in the late 2020s. And that will just be an incredible milestone, a giant leap forward for microlensing that will find so many new planets. And what's special about microlensing is its sensitivity is unique amongst all the planet finding techniques. Whereas the radial velocity method and transits are biased towards planets close to the star, microlensing conveniently fills in a sorely needed gap to be filled in between 1 and 4 astronomical units.
You're listening to Are We There Yet? I'm Brendan Byrne. We're speaking with MIT's Sarah Seeger about how new technology is aiding in the search for exoplanets, planets that exist outside our solar system. In this particular case, would this microlensing be used to look at stars that are already confirmed to have exoplanets to see if there are even more farther away from the star?
No, actually, it's a new population of planets. The methods we have now, we're studying very close by planets. I know it sounds strange, astronomically speaking, but for astronomy, far is close, like tens of light years, hundreds of light years is literally right next door. But these stars will be much further away. They'll probably be like kiloparsecs away, maybe thousands of parsecs away. But what's unique about it is they'll be able to find the kind of planets we can't find yet. And why is this so important? Because believe it or not, with all the methods we have today, it's extremely difficult to find anything like a solar system copy. So despite having thousands and thousands of known exoplanets, we don't know how common our solar system is or exactly how rare it is. We know it's rare, we just don't know how rare.
And what is it on the Nancy Grace Roman Space Telescope that is allowing you to see this lensing? Is it that these sensors are just super, super sensitive, or is it looking at a different field of light?
This telescope is designed to be very wide field. And because microlensing events are incredibly rare, it's that ability to see a giant area on the sky that lets it perform its job.
That's absolutely wild that you're looking at these exoplanets that are actually bending space, and that is how you are confirming. It's fascinating. It's so cool.
Well, hopefully we can figure out, how common other solar systems are. It's kind of crazy to be in a very maturing field without knowing the answer to that basic question.
Did you ever imagine this, Professor Seeger? I know that the first exoplanet was confirmed in the 1990s, and now here we are in 2024, and we've got thousands of candidates. Like, this is moving extremely fast. What is it like to be on the cutting edge of discovery like this?
It's pretty incredible. I mean, think about it. We went from just having science fiction like Star Wars and Star Trek and other movies to then having real planets, but being so limited. It's like so limited in being able to find only the hot Jupiters, planets so close to their star. And now, with everything unfolding so rapidly, it's crazy. It's like a dream.
Early in your career, you developed the frameworks to uncover what these atmospheres were made of these exoplanets, and now that is something that we are seeing thanks to things like JWST. What is it like for the field of exoplanet studies to not only know that these things exist and what their masses are, but potentially know what the composition of their atmospheres are? How does that help you understand what they are?
There's so many things I could tell you about in this respect. We have the new James Webb Space Telescope that has been successfully operational for a few years now, and it's literally taking us to the next level. It is helping us study exoplanet atmospheres. There's so much going on. I mean, one of the biggest questions in exoplanets is, remember how we said their solar system copies are rare? It means other things are common. And what appears to be the most common planet in our galaxy, as far as our telescopes allow us to determine, are planets between the size of Earth and Neptune, for which there's no solar system counterpart. We don't know what they're made of. We don't know how they formed. And it's just crazily mysterious. People are hoping that by observing the atmospheres of these so-called sub-Neptune-sized planets, we could try to figure out what they are. Are they a water world, like a scaled-up version of one of Jupiter's icy moons? Perhaps they're a giant rock surrounded by hydrogen and helium. Maybe they have such a massive hydrogen-helium envelope, acting like a giant greenhouse, that this massive rock is even melted on the top and having a magma ocean beneath a hydrogen-helium envelope. So we're trying to sort through all of those things right now. And let me say the other big question that we think we can answer in the immediate future is whether or not some planets orbiting M-dwarf stars, the stars that are smaller and cooler than our sun, that also give out giant amounts of energy in their early phases, we want to know if the rocky planets orbiting M-dwarf stars even have atmospheres.
Huh, that is interesting. Crazily mysterious. I love how you put it that way. As a scientist, is that frustrating that you're finding things that you've never seen before?
Yes, it's like a lot of things in life. You know, do you ever come across a roadblock and you just are devastated? And then you slowly kind of get used to the idea and then you try to make the most of it. So what happened was, back when these first sub-Neptune-sized planets were discovered, we realized they're of an average density that we cannot pin down what they're made of from their density alone. Like, let's imagine for a moment, I tell you that I have 3 planetary materials. I have iron rock, I have water, and I have hydrogen and helium. And I'm going to give you a box, and your job is to tell me which one. Those are 3 common planetary materials. So if I hand you a box, and wow, it's so heavy it just falls to the floor, which option would you pick? Now let's imagine I give you a box, and wow, before you know it, it just floated away. It was so light. Now which one?
Of the lighter one, right?
Yeah. Now, if I were to give you a box and I hand it to you, and it's just so average, it's super average, it doesn't sink to the ground, it doesn't feel heavy, it doesn't feel light. Now, if you think through that, you literally can't tell me what it's made of because there are many options. It could be a mixture of rock and hydrogen helium. It could be mostly water. It could be some combination of all 3. And that's what happened, was we were crushed that the mass and the radius, therefore the average density, we'd never know what they're made of. We just had to find a positive. It sounds kind of lame now that I'm explaining it to you, but our positive was we just used a mathematical framework that could constrain all possibilities. So even though we couldn't say what it was, we took some joy in being able to say, look, here are all the possibilities constrained by this beautiful mathematical model. So today we're hoping that the atmosphere can help sort through it. But so far, it's been a bit tricky to do that. So that's kind of all really happening right now, and we'll have to get back to you on the answer.
Still to come, could life exist on other planets?
What we can search for in terms of a sign of life can often be mimicked by other things, like volcanoes or lightning or meteoritic delivery. And so it's very hard for us to say anything robust. But the good news is there's more and more activity. There are more and more bodies in the solar system we think might harbor life. and exoplanet atmospheres is accelerating.
Our conversation about exoplanets with MIT's Sarah Seeger continues. That's ahead on Are We There Yet? You're listening to Are We There Yet? I'm Brendan Byrne. Our rover friends on Mars have been busy exploring the dusty red planet, and NASA is exploring two ways to bring samples back to Earth. We catch up with University of Florida's Amy Williams about what Curiosity and Perseverance have been up to these days and the plan to bring samples back from Mars. That's next week on Are We There Yet? Stay listening. But for now, we're talking about exoplanets, planets that exist outside our own solar system. One big question remains as we talk about exoplanets. Could some be habitable worlds? Last year, NASA sent a mission to Jupiter's icy moon Europa because there is evidence the moon may have the building blocks for life on and under its surface. Could these elements be on other faraway planets? And while we are finding these exoplanets, could we potentially have missions like Europa that send a vehicle to these worlds to explore? Our conversation with Sarah Seeger continues. And Professor, the amounts of, or I'm sorry, the number of atmospheres that you surveyed is far smaller than the amount of candidates, right? So you have very, very small sample size of what these atmospheres are, correct?
Correct. So we know of thousands, many thousands of exoplanets, with thousands more waiting to be confirmed. Maybe about 100 or 200 atmospheres have been attempted to be studied. Maybe about 2 or 3 dozen have been studied in some detail. But things take time. And, glass half full, glass half empty, we're happy. This is huge. We're getting more and more every month.
Exoplanets exist outside of our solar system, but you're also leading a charge on looking for habitable worlds inside our own solar system with the Venus Life Finder. Can you tell me a bit about what you're hoping to answer with this mission?
Yeah, so I first wanted to give you the briefest encapsulation of how I went from working on exoplanets to also working on Venus. And this came about because my team had been studying every possible molecule that might be a good biosignature gas candidate for future searches for signs of life on exoplanets. We have had an idea for 100 years in astronomy that we should be looking at atmospheres of other planets. And 100 years ago, they weren't thinking of exoplanets, presumably our solar system. And oxygen, for example, in our planet Earth is here to 20% by volume. But without life, without plants and photosynthetic bacteria, we would have no oxygen. It's so reactive, it shouldn't be there at all. So we're looking for gases and atmospheres far away, gases that are so reactive, they shouldn't be there in context with the rest of their environment. Well, one of our favorite gases we came across in our computer simulations is a gas called phosphine. Now, phosphine is an amazing biosignature gas. We humans make it as pesticides. Life in oxygen-free environments makes it, but it's really not really made in any other way. And it turned out when we were working on this, another team across the ocean, led by Professor Jane Greaves, was actually purposely searching for signs of life on Venus by way of the gas phosphine. So someone connected our two teams, we got together, we made an announcement, a reported discovery of phosphine on Venus, that it was a gas that didn't belong, that couldn't be explained by lightning or meteoritic delivery or volcanoes or anything else we could think of to the amount seen. And this discovery, you may remember, became incredibly controversial and to this day remains very controversial for a lot of different reasons. So I'm sure you remember the story about phosphine on Venus.
Yes. And I believe we talked about it the last time we had on. But yes, it was controversial in the fact that you have to confirm that it is actually created in a different way, right?
Right. Well, we can come back to phosphine later if you're still interested, but let's just say that phosphine did a wonderful thing. It shone a new light on Venus, revived interest on Venus, brought new people into the field, and now it's no longer about phosphine. Because guess what? Unlike an exoplanet, Venus is right next door. And we literally could send sophisticated instruments to look for very complex molecules that might indicate there's life. So, not byproducts of life, but the building blocks of life itself. And that's what my team aims to do eventually.
Hmm. And how would you have to go about doing that? What would this probe be?
Well, just to zoom out a little bit, we spent some time in 2020, 2021, all up until now, trying to answer that question. And it's a super hard question. Because when you go to space, you want to build something quote unquote dumb, like something with as few moving parts as possible, with the least complexity as possible. And so we're doing that with our first mission to Venus. It's called we call ourselves the Morningstar Missions to Venus, an international consortium to send a series of missions to Venus. And our first mission we call the Rocket Lab mission to Venus. This is a small, simple, cheap mission. And this mission will not find signs of life, but it will investigate the cloud particles, where if there is life, it should be in the cloud particles. And that mission we can talk a bit about, but we're preparing for our next mission, which would be much more complex. It would be a balloon mission to Venus, a balloon that would last about a week and that would float at an altitude of around 50 kilometers. And it would have an instrument on it called a mass spectrometer, a special mass spectrometer. It's called the Origin instrument, ultimately originated in Switzerland. And this mass spec puts a very gentle charge. It has to do something to the molecule to get it ready to figure out what it is. But many of the past methods have just, they fragment the molecule and make it very complicated to know what the original molecule was. So it would have to be a balloon floating in the atmosphere for about a week, collecting the cloud particles and delivering them to the mass spectrometer to see if there's any very, very complex molecules, so complex that they might be associated with life.
Hmm. That is fascinating. You're listening to Are We There Yet? I'm Brendan Byrne. Our conversation with MIT's Sarah Seeger continues about finding the building blocks of life, possibly on faraway worlds known as exoplanets. I want to talk about that first one, the Rocket Lab um, probe. Obviously, Rocket Lab is a private space company. Um, does the commercialization of space or access to rockets from companies like Rocket Lab make it a little bit easier to get these missions, pardon the pun, off the ground in the first place? Does the fact that you have greater access to a ride off of this planet make it easier for missions like the Venus Life Finder to, pardon the pun, get off the ground?
Yes, we're hoping it will. And one of the reasons we call ourselves the Morningstar Missions to Venus is sometimes Venus shines very brightly in the morning sky, like a new dawn is rising. We're hoping to change the attitude that we don't have to wait 4 decades to go back to the atmosphere of Venus or any other planet, but hopefully that there is a way to do more frequent, smaller, cheaper missions. And that's largely due to new space, to these new commercial companies that have changed the way we're doing space. So we hope it will. It is definitely tricky, though, to get money, but we're hoping it changes.
Hmm. And the ultimate question: are we alone in the universe? These you know campaigns to study exoplanets. We're looking for habitable worlds outside of our solar system. You're looking for signs of life on Venus. What are the prospects of scientists like yourself from answering that question? Are we alone? Are there other places in our universe that could harbor life?
I wish I could give you a straightforward answer and a compelling one that we're going to solve this problem. But the reality is, it's so incredibly complicated. And it's made more complex by the fact that what we can search for in terms of a sign of life can often be mimicked by other things, like volcanoes or lightning or meteoritic delivery. And so it's very hard for us to say anything robust. But the good news is, there's more and more activity. There are more and more bodies in the solar system we think might harbor life. And exoplanet atmospheres is accelerating.
And what is the next big thing you are keeping your eye on, Professor Seeger? What is going to be the next groundbreaking tool or mission that is going to get you closer to answering that question?
Well, we're first waiting to see if the planets orbiting or transiting M-dwarf stars actually have atmospheres. That's kind of the number one thing the community is after right now. Next, we'd like to know if any of them have liquid water on their surface, needed for all life as we know it, although we also think life can exist in non-liquid environments. So I think it's really the big thing is maxing out on the James Webb Space Telescope for what it can do. But beyond the James Webb, we're always investing in the next big thing. And the next big thing is quite far off, actually. But it is our ability as humanity to discover a true Earth twin. That's an Earth-sized planet in an Earth-like orbit about a sun-like star. That's an incredible challenge because our Earth is so tiny, so low mass, and so faint compared to our sun. We'll need to go above the blurring effects of Earth's atmosphere with a special telescope that can block out the starlight so we can see the planet directly, see the atmosphere, and find our true Earth twin. Because we'd like to find another Earth to know if there's another one of us out there somewhere. And that, at the moment, takes the form of NASA's Habitable Worlds Observatory. But it's still shaking out as to what exactly that telescope is, how much it's going to cost, how long it's going to take. And so that's the next big thing.
Mm-hmm. Well, we will have you back on to chat as we get closer and closer to that mission. Sarah Seeger is professor at MIT. Sarah, thank you so much for joining us.
Thanks for having me today.
That's going to do it for this week's show. If you're not already, be sure to subscribe to the show's podcast feed so you never miss an episode. Do that on Apple Podcasts, Spotify, the NPR app, YouTube, really wherever you get your podcasts. Stay connected with the show. Follow us on social media. We're on Instagram and Facebook, AWTY Space. And if you got an idea for a future episode of the show, or you want to join us as a guest, reach out. Our email is arewethereyet@cfpublic.org. More space coverage online. Visit cfpublic.org/space. Are We There Yet is a production of Central Florida Public Media. Our producer is Marion Summerall. Our intern is Allison Castillo. Editorial guidance from LaToya Dennis. Support for Are We There Yet comes from our listeners. Until next week, I'm Brendan Byrne. Thanks for listening.